give a lecture, the change in CTO deflection toughness of the structure still by press strain and dynamic loading. The lead author, Dr. Egi, couldn't come today because of his another business. So that's why I am asked to give lecture as a substitutional lecturer. So do not ask me the detail. Okay. So anyway, because the Professor Minami give us the very detail of the background, so I have nothing to introduce newly here. But my talk just focus on the toughness degradation due to the large strain in cyclic loading and the high strain rate due to the earthquake. And also, this is also explained by Professor Minami. This is the out frame of WES 2808. And my talk is related to this red column. That means that the final goal is toughness degradation, which is described by the transition temperature rise due to the dynamic loading and also the press training coming from the cyclic loading. Okay, this is the schematic drawing of the CTOD toughness transition curve. This is the body material. Because of due to the dynamic loading and also press training, those factors induce the toughness degradation and transition curve are moved to the higher temperature. And also, in case of the earthquake, we need to pay much attention to the combined effect of the dynamic loading and press training. And here we will define the temperature rise, transition temperature rise to the dynamic load due to the dynamic loading as delta TD, and delta TP is defined as the temperature rise due to the press training, and also the combined case. The temperature rise is called as a delta TPD, a little bit complicated, pay much attention. And we conduct experiments and materials, all 5 kinds of the scale with the from the strength of 490 to 780. And we conduct the huge number of CTOD tests using this specimen size. And some specimen, some group is conducted directly the CTOD test using the different, 3 different loading rates. And another group is once we apply the press training up to the 10% within a uniform elongation, no necking, and also export to the CTOD test and the different loading rate. And this is an experiment. Results. A little bit complicated, so I will not explain the detail. However, this is the result of 490 megapascal class steel. The top 3 is the SM490A, and bottom one is the SN490B. And left-hand side is the, these open mark correspond to the virgin material, CTOD. And solid one in the left-hand side is the CTOD result after press training. And middle one is the similar expression. The solid one is the CTOD after under the dynamic loading. And the right-hand side is the almost a similar expression, but the solid marks coincide with the CTOD result with a combined effect of the dynamic loading and press training. And case of the 570, it's the same. And so I will skip the detail. And 780 megapascal plus steel, that is the same. And returning back to the 490, it's easier to explain. That you can see comparing with the virgin material, the press strain enhanced the transition temperature rise, and also the dynamic loading. is also. And of course, that in case of the combined effect of the restraining and dynamic loading, push up the transition temperature. And that's why from the overview of the experimental results, in case of the transition temperature rise, in case of the combined effect of the effect is larger than the similar temperature rise of the individual effect of the prestrain and dynamic loading. And final target of us is how to evaluate the transition temperature rise and the combined effect of the prestraining and dynamic loading. And the most simple idea is just superposition. This figure shows that the horizontal is the transition temperature rise due to the combined effect of the prestraining and dynamic loading, and the vertical axis shows that just the sum of the temperature rise, which is induced by individual effects. So this is the result for 490 megapascal class steel, and right hand side is a rather higher strength steel. In this case, you can see that there are no simple additional rule of the individual effect. So we need to make another idea to estimate the transition temperature rise, which is induced by the combined effect. So that's why the WES 2808 proposed the reference temperature concept. So as I mentioned, using the experimental data, the prestrain and dynamic loading induce a toughness degradation, right? And push up to the transition curve. Based on the local approach, the fracture toughness can be described by both the stress distribution at the crack tip, in other words, the driving force, and also the critical fracture strength, such like critical wave stress. And another research has already clarified that the critical strength does not change so much due to the prestrain and dynamic loading. So that's why these toughness degradation due to these factors surely coming from the stress distribution enhancement at the crack tip. So the stress distribution at the around the crack tip can be related with the flow stress of the material. And it is well known that in case of the prestrain and dynamic loading, usually induce the enhancement of the yield strength and tensile strength, as Shimada already mentioned, using the experimental data. And also, Mr. Shimada introduced some of the empirical formulation which described the YP and TS as a function of the prestrain and also the strain rate. So that's why we try to make a relation between the transition temperature rise and flow stress change relation. So that's why we examine by experiment. So this figure shows that the vertical is that the transition temperature rise, and the horizontal is the flow stress change for the experimental data for prestraining, dynamic loading, and combined effects. And left hand side is a 490, and right hand side is a more stronger test plate. So that just looking at the experimental trend, this transition temperature rise is very sensitively increased in the smaller flow stress change range here. But however, beyond a certain flow stress change level, the increase of the transition temperature rise gradually saturated. But maybe this is caused by the local temperature rise at the clock due to the dynamic loading. But anyway, the WES 2808 propose this blue bilinear approximation from the viewpoint of the engineering judgment. But my talk up to here is just a monotonic press training. But the final target of us is the press train in cyclic loading. So we need to investigate how to estimate the press train level due to the cyclic loading. So the WES 2808 proposed a skeleton strain concept. The skeleton strain is a summation of the plastic strain increment, which induced by the stress over the peak stress in previous loading cycle. And actual fracture is usually triggered in tensile part in cycle, right? That's why the compressive, this one, the summation compressive skeleton stress is this blue curve. And to the fracture cycle shall be considered. But however, we have the another problem, that the tension after compressive press strain usually induces the Barzinger effect. So this is one of the experimental stress strain curve. These round stress strain curve is coincide with the tension after compressive press training. And this stress strain curve with the clear elbow point coincides with the tension after tensile press training. So due to the Barzinger effect, the flow stress change in compressive press strain will be smaller than the smaller than the flow stress change after tensile press strain. But however, on the other hand, the CTOD toughness degradation due to the press strain are the same, independent on the compressive tensile press strain. This figure, the horizontal is the transition temperature line due to the tensile press strain, and the vertical is the similar temperature rise due to the compressive press strain. So you can see that independent on the compressive and tensile press strain, that the transition temperature rise can be described by just as a function of the applied press strain level itself. So that's why the WES 2808 proposed that the flow stress change for tensile press strain is used even in the subjective compressive press strain. And this is the final examination test results. This figure shows that the vertical is the transition temperature rise, and horizontal is the total amount of press strain level. And this figure compared the result between the monotonic press strain and the cyclic press strain. Of course, in this cyclic press strain case, we use the skeleton strain concept. The when press strain level is evaluated by skeleton strain in cyclic loading, the transition temperature rise, delta TPD, due to the cyclic press strain is similarly evaluated to monotonic press strain. Okay, so let me summarize that, my talk. The most important is the reference temperature concept. And this difference temperature concept, the delta TT, that is the transition temperature rise is needed. And also this transition temperature rise is related with the flow stress change. Because the flow stress change to be easily evaluated by the empirical formulation. Thank you for your attention.